quantum mechanics is confusing, non-intuitive, and seemingly nonsensical. What I found through my journey is that this confusion and senselessness isn't a bug, but a feature, and creates a new way to see our everyday life. Instead of interpreting quantum mechanics, I ultimately realized maybe we should just submit to it and let quantum mechanics interpret our own lives. Hey there, I'm cosmologist, NASA advisor, author, and host of the Ask a Spaceman podcast, Paul Sutter. You can find links to all my work and order my latest book, Rescuing Science, Restoring Trust in an Age of Doubt, on my website, pmsutter.com. Go check it out if you're into all things space and science and the intersection of art and science. Today, we'll be reading How I Learned to Stop Worrying and Love Uncertainty by yours truly. It's a piece near and dear to my own heart from Nautilus magazine, and discover why Heisenberg and Schrödinger are less like physicists and more like therapists. So let's go. Like most physicists, I spent much of my career ignoring the majority of quantum mechanics. I was taught the theory in graduate school and applied the mechanics here and there when an interesting problem required it, and that's about it. Despite its fearsome reputation, the mathematics of quantum theory is actually rather straightforward. Once you get used to the ins and outs, it's simpler to solve a wide variety of problems in quantum mechanics than it is in, say, general relativity. And that ease of computation and the confidence that goes along with wielding the theory mask most of the deeper issues that hide below the surface. Deeper issues like the fact that quantum mechanics doesn't make any sense. Yes, it's one of the most successful, if not the most successful theories in all of science. And yes, a typical high school education will give you all the mathematical tools you need to introduce yourself to its inner workings. And yes, for over a century, we have failed to come up with an alternative theory of the subatomic universe. Those are all true statements. And yet, quantum mechanics doesn't make any sense. The statements that quantum mechanics makes about the subatomic world fly in the face of our natural intuition about the macroscopic world. If I throw a ball at you, you have a decent shot of catching it because you know it will only take a single path. If we make plans for dinner, we don't need to worry about what the Andromeda galaxy is doing right now because it's very far away and thus very unlikely to interfere with our plans. If you see someone walk through your doorway, then you can say with confidence that they did, in fact, walk through your doorway. And yet, all these very reasonable statements break down when we examine the subatomic world. Particles can exist in multiple states at once. They can travel multiple paths at once. Particles can suddenly appear in unexpected places. Particles can maintain a phantom-like connection to each other, known as entanglement, regardless of the distance of their separation. We can't make confident predictions about the outcomes of experiments, but instead have to rely only on fuzzy probabilities. There are fundamental limits to what we can know. When I first learned the full extent of quantum weirdness in school, my brain broke, along with my expectations of how the world works. My first reaction was amazement and wonder at the richness and complexity of the subatomic world. And then, dismay, heartbreak, confusion, torment. A storm of emotions poured over me as I tried in vain to go from awestruck wonder to considered understanding. While my undergraduate and graduate courses on modern physics and quantum mechanics were teaching me these fundamental statements, they didn't discuss to any significant degree the deep philosophical problems that those statements entail. That kind of reckoning, in my case, didn't come until over a decade post-PhD. As I struggled with the philosophical side of quantum theory, many years after I should have, I discovered to my surprise and relief that my struggles were mirrored in the very historical development of the field itself. Quantum mechanics is confusing, non-intuitive, and seemingly nonsensical. What I found through my journey is that this confusion and senselessness isn't a bug, but a feature, and creates a new way to see our everyday life. Instead of interpreting quantum mechanics, I ultimately realized maybe we should just submit to it and let quantum mechanics interpret our own lives. But in order to arrive at this somewhat unorthodox but ultimately liberating vantage point, I had to journey through the 4 stages of what I have come to call quantum grief. The first mystery I encountered as an undergraduate of the hidden secrets of the subatomic realm was the bizarre feature of reality called wave-particle duality. In the macroscopic world described by classical physics, the physical view of the world prior to the invention of quantum mechanics, there are 2 kinds of objects: waves and particles. Particles are generally small, well localized in space, and have a defined, measurable position. If you wanted to, you could point to a particle, and everyone would know that you're picking out that particle and not another one. Waves, on the other hand, without a particular place in space, are just kind of over there, vaguely. It's much more difficult to point to a wave. Waves also don't zoom from one place to another, but instead slosh around in complicated patterns. In this classical view of the world, all fundamental entities are either one or the other. To my undergraduate brain, this simply made sense. But in the quantum view, all objects have properties of both. A single object can sometimes act like a particle or sometimes act like a wave, having wave-like properties in one moment, say when an electron scatters off of an obstacle, it acts like a wave would, and a particle-like property in another. When that electron finally hits a detection screen, it deposits all its energy in a specific location, much like a particle. I had read about this in books as a teenager, but in college I had to confront it head-on in a formal, impossible-to-ignore setting, and it blindsided me. The only response I could conjure was a simple, how? The wave-like nature of matter doesn't manifest itself at macroscopic scales, which is why physicists didn't notice this until they started playing around with subatomic particles at the beginning of the 20th century. Much like my first taste of the phenomenon, when the early quantum pioneers initially encountered wave-particle duality, their first response was complete and total confusion. What exactly is a wave of matter? How are we supposed to interpret this now experimentally undeniable aspect of reality? I would look at my own face in the mirror. Quantum mechanics taught me that what I saw had some very tiny but very real wave nature. But a wave nature of what? My reflection couldn't give me an answer. Physicists like Erwin Schrödinger, working in the first half of the 20th century, argued that at tiny scales matter was literally smeared out over space like a wave. He believed that if we could crack open an atom and look at its bits and pieces, we would see tiny little waves wiggling about. Schrödinger would use this insight to develop a wave-based theory of quantum phenomena that was astoundingly successful in describing a wide variety of otherwise perplexing experimental results. But Schrödinger was not alone amongst the explorers of the unknown quantum land. Other physicists, like Werner Heisenberg, working around the same time, argued that we shouldn't bother even trying to build up a mental picture of what subatomic particles are up to, and should instead just focus on experimental results. He developed a completely different paradigm for answering quantum problems. His method was based on much more difficult mathematics, but was nonetheless equally successful. Cue heated debate, with Schrödinger snubbing Heisenberg's approach as nonsense because what good is a physical theory if it can't paint a picture of the world, and Heisenberg slamming Schrödinger, saying that subatomic physics is so far beyond the realm of human perception that our normal classical thinking is obsolete. Eventually, Schrödinger's ideas fell out of favor, as experiment after experiment revealed that subatomic objects like electrons, while they had wave-like properties, most definitely did not extend through space. By the 1930s, the initial confusion over the onslaught of experimental evidence and theoretical tools eventually gave way to a sort of quantum orthodoxy. This mirrored my own experience beginning in graduate school. Aspects of the quantum world, beginning with wave-particle duality, fly in the face of common sense, logic, and our natural intuitions about the world. But then, just when the confusion reaches a crescendo, and it seems like the feeble human intellect will be swallowed by the quantum tempest, comes sweet conceptual deliverance. A formalism. The relief I felt when I finally learned the postulates and mathematical framework of quantum mechanics is nearly indescribable. It's like this wonderful escape hatch, liberating yourself of the mental burden of trying to untangle the Gordian knots of quantum reality, set free to dance through the blissful fields of getting work done. In the 1930s, physicists like John von Neumann would take the various initial attempts at quantum mechanics and craft it into a cohesive, rigorous whole. Finally, after decades of study, we had a firm physical theory based on a limited set of founding postulates, a full mathematical language for writing down problems and finding their solutions, and a wide variety of interesting applications to tackle with the theory. The nature of atomic absorption and emission, the building blocks of chemical and nuclear physics, the creation and manipulation of fundamental particles, and so much more. We had a physics of the subatomic world. The interpretation of what the mathematics said about the world slid away from the hopes of Schrödinger and fell firmly into the Heisenberg camp. Don't worry about the details and just focus on solving problems. The wave-like nature of particles was demoted into a mere mathematical trick, a way of calculating probabilities rather than an extant property of nature. Other results of the wave nature of matter, like entanglement or spooky action at a distance, were accepted as straightforward facts without any deeper discussion about what that entailed. Quantum mechanics was weird and made no sense, but it worked, dang it. And in that work, I found safety. I didn't have to worry about mysterious quantum this or that, about what was actually happening, as long as I could keep putting the mathematical pieces together. It felt good to solve problems, to find interesting applications. As a physicist, I developed a new kind of intuition, one not based on growing up a living, thinking macroscopic creature, but an instinctual grasp of the symbols and machinery of quantum mechanics. I began to intuit which problems were well suited to the theory and which ones were not. I found myself able to cast meaningful physical questions about the real world into the language of von Neumann, and amazingly, get an answer, a result that I could test against experiment, as I and my classmates did in the lab sections of our classes. I began to believe that I finally had a firm grip on understanding quantum mechanics. That is, as long as I didn't think too hard about what it all means. The siren song of quantum formalism, the raw math, was all too tempting. But follow it too far and you are bound to crash into the sharp, unyielding rocks of a deceptively simple question. What does quantum mechanics actually mean? Schrödinger had his doubts. So did Einstein. So even did Heisenberg and Bohr and Dirac and von Neumann and all the other founders of quantum theory. The difference is that Schrödinger and Einstein would go to their graves believing that quantum mechanics was incomplete, while the others held onto the slim comfort that our physical theories had finally taken us to a place that we could not otherwise mentally comprehend. But at least we could get answers and validate against experiment, which was good enough. The dominant interpretation of quantum mechanics is called the Copenhagen interpretation. If you've ever done any reading on this subject, you've probably encountered it already. It's the default assumption of how quantum theory should be viewed, and it's the default treatment given in a typical physics education, including mine. At its highest level, the Copenhagen interpretation instructs us not to sweat the small stuff and just focus on the math. Matter has a wave-like property that maps out probabilities for the outcomes of experiments. When we perform an observation, that wave and all those probabilities snap out of existence to be replaced with a single result in our apparatus. Aspects like fundamental uncertainty principles and non-local entanglement are simply facets of the full theory. How does it all work? Why do the waves snap out of existence upon measurement? How can two distant particles be aware of their entangled partner without exchanging information? What is the state of reality when we're not observing it? These are all questions that the Copenhagen interpretation ignores because it says they're not important. What matters is results, results, results. And so I, ever the lifelong student, had to eventually confront the Copenhagen interpretation and its explicit lack of desire to explain anything further. Some physicists are fine with this, choosing to shut up and calculate and accept that our puny human brains can't possibly imagine or envisage what's happening at the subatomic level. And many I know find a sort of comfort in that. Other physicists are less fine with this. Thankfully for them, there are plenty of other interpretations to choose from. Some elevate the wave-like nature of matter to a real entity. Some claim that consciousness plays a critical role in the measurement process. Some say that it's all an illusion of shifting information. There are more. Dozens of potential interpretations, all selecting some parts of quantum theory to be true and other parts to be mere mathematical artifacts. For some physicists dissatisfied with the aloofness of the Copenhagen interpretation, they find refuge in these alternative interpretations. I did not. The interpretations of quantum mechanics try to make sense out of the nonsense by applying a layer of rationality on top of the bare mathematics of the theory. A bedtime story to help us sleep at night when we can't stop thinking about how strange the subatomic world is. I myself tried to find salvation in interpretations, years after learning the theory itself in graduate school, hopping from paper to paper like a neophyte trying out different religions. Ultimately, I couldn't find any interpretations that were satisfying. The classic Copenhagen left a sour taste in my mouth for its refusal to paint a portrait of subatomic processes. I believe that humanity is smarter and cleverer than Heisenberg gave us credit for. But the other interpretations have their own shortcomings. For example, if you follow the logic of making the wave nature real, you end up with parallel universes constantly splitting into existence, with no further explanation of how that's supposed to work. And so on and so on. For every interpretation, there are some attractive features to it and some parts of its own theory that it fails to explain. So what was I to do if none of the interpretations seemed to satisfy that deeper craving to live in an understandable universe? One answer is to retreat back to the safety of the Copenhagen interpretation, finding solace in the mathematics and giving up on the dream of visualizing subatomic processes. Another is to dig deep into one of the alternative interpretations, believing that with enough work and enough cleverness, I could overcome their shortcomings and build a coherent, consistent, complete model of the universe. There is another way, one that I found after years of frustration, and that is to completely subsume myself into the weird and wonderful quantum world, embracing the ultimate lessons of the theory. We have tried for over 100 years to force an interpretation on the theory to no avail. So perhaps that's nature trying to tell us something, that no interpretations are available to us. The experimentally verified reality of quantum mechanics is indeed that classical thinking, based on our intuitions of the macroscopic world, is inadequate to describe every aspect of the cosmos. And trying to create an interpretation and insist that it's the correct one, even the Copenhagen interpretation, is precisely the trap of classical, binary, yes-no thinking that the subatomic world is trying to tell us to avoid. Here's the mental model I eventually settled on after years of apathy and antipathy. Instead of trying to make sense of the quantum world, let's use the quantum world to make sense of ours. Thinking about quantum behavior seems absurd, but that's only because we live and breathe in a classical world. So what if we tried to live in a fully quantum one, even in our everyday lives? When I released myself from interpretation, I found the freedom to see the fundamental lessons of quantum mechanics, probabilities, uncertainties, non-locality, entanglements, and so much more, and apply those lessons to my life. For example, I could begin to live my life truly accepting the uncertainty of the future, setting goals and visions without the burden of concrete expectations. I could acknowledge that my actions had influence across the globe, with even small gestures of kindness or charity making an impact. I accepted that I can't know everything as well as I wish I could. I stopped myself from falling into binary either or choices, allowing situations, choices, and even people to be more complex than that. As I continued to put these thoughts into daily practice, I found that Schrödinger, Heisenberg, and the rest sounded less and less like physicists and more like therapists. Indeed, nothing I had learned was a new revelation to mental health professionals. These were useful lessons that enriched and informed my daily life. Through a quantum lens, I found happiness, contentment, satisfaction, and a better sense of my own humanity. It wasn't easy, and it still isn't. I still feel the occasional classical tug to insist on an interpretation, or to finally get to the bottom of all this quantum nonsense. Every day I have to wake up and resist those temptations and remind myself that the quantum world, the real world, is so much more rich and vibrant and wonderful than that. Thank you for listening along. If you're interested in more deep dives into quantum mechanics, physics, cosmology, astronomy, and everything in between, you can follow me on Instagram and YouTube at Paul M. Sutter or on X at Paul Matt Sutter. You can also visit my website, pmsutter.com, for direct links to my work, my books, my podcasts, and so much more. Go check it out and have a great quantum day.